All right, let's get going. 6.6, building quadratic functions to describe situations. So make sure you guys are listening because if you're just flying through and just copying things down, you're not actually learning. You're just mimicking, which is sad. So let's get going. All right. A cannon is 10 feet off the ground. It launches a cannonball up into the air at 406 feet per second. It's not too fast. Imagine there is no gravity. Ooh, so that's changing some things for sure. That cannonball continues to travel upward with the same velocity. Yeah, that's a big deal. So let's look at this table and try to understand how we should approach it. So you start off at 10, and it's traveling 406 feet per second. So you're just going to be tacking on an extra 406. So go ahead and remember, gravity's not there. So will you be adding the 406 uh, to the height of this cannonball as it flies by every second? All right. So go ahead and finish that table and pause the video. So pause it. If your friend's just kind of ignoring you and not pausing and already just flying through, just be like, "Hey, pause it. Figure it out." All right. Thanks. So again, pause it. Okay. So hopefully you pause the video and you finish the table. And you're right. If you ended up getting something like this, so 416 for the first one, and then you constantly keep adding 410, or no, 406. Apologies, 406 feet, and you start getting something going on like this, right? 1634, and then 2040. So gravity's not pulling this thing down at all. It's just going off like crazy. Now it's constant, isn't it? It's constantly adding by 406 feet, and that's because of its velocity, right? So you start at 10, and you keep increasing by 406 feet every second, or t times. Okay, so is this linear or exponential or quadratic? What do you kids think? So go ahead, discuss it with your group. Is this linear, exponential, or quadratic? Go ahead and pause. Okay, so hopefully you guys said it's linear, right? Because it has a constant rate of change of the 406 feet per second. It's not spiraling out of control, is it? All right, so write an equation to model the distance in feet. So in terms of d in t seconds. So it's very similar to the one I already wrote in the table, but go ahead and try doing that on your own. Press pause. All right, hopefully you press pause and you tried creating your own equation. You should get d equals the 10 for your initial height of when the cannon was fired, and the plus 406 per second, which is in terms of t. So if you got that, good job. All right, moving on. All right, so tracking a cannonball. So this one's going to take you somewhere around 15 minutes. We'll see about that. And earlier, again, we did a cannonball in feet where there was no gravity. Um, but let's see, this table shows the actual heights of the ball at different times. So it looks like we're comparing this table with the table we completed earlier. So um, let's try to recall again the table back here, right? The 416, 822, all up to 2040. If we do that, go ahead and use the graph to kind of do that. So let's graph the this one right here, 0 comma 10, still somewhere down here, right? 1 comma 400, somewhere around there. 2 comma 78, and you guys get the idea. All right, so go ahead and pause the video and then finish graphing or plotting this table onto the graph. So pause it. Okay, so if you were done pausing it, you should plotting this. Um, you should get something like this. This is not perfectly exact, but I'm trying to eyeball it here. Okay, that's not where I drew the dot. There we go. And 13 something something seems like that's right around here. And then 16 4 somewhere around here. Okay. So again, those were the plotting for that. If you plot the table, though, all right, and let me use a different color here. Let's use blue. So if we use the old table, we had 0, comma 10, which is same area. Um, and then we had the 4. What was it? The 4. I'm trying to remember. I'm scrolling up. 416. Okay, so that's that one. And the 822, it's somewhere around here, right? The was it 1228, somewhere around here. The 1634, whoa, it's like right up there. And the 2040. So as you guys can see, um, these without gravity, right? Your cannonball is definitely going way out there. So you can kind of see how gravity is not pulling on the first cannonball because there's no gravity. That's a big difference between the one that does have gravity and the one that does not. Now the question is for you is how are the two graphs alike? How are they different? So go ahead and discuss with your friends about that in your group. All right, so go ahead and pause. All right, so now that you unpaused, how are the two graphs alike? How are they different? Again, I kind of already discussed it. Um, they're both going up, they're both increasing, they're both representing the same thing, except different contexts. One cannonball has no gravity pulling down on it as it's flying through the air. The other one does, and you can actually see it curve because of the gravity. So one is linear, right? The blue one is definitely linear. But what about the newest one? What? So go ahead and discuss this with your group. Which one is this? Is it linear? The red one, the new one, the one with gravity. Is it linear, quadratic, or exponential? And go ahead and pause. Discuss that. Okay, hopefully you unpaused it and you mentioned and discussed how it's quadratic, right? Because it's curving down, which is kind of nice. It's gravity pulling it down, right? All right, let's write an equation to model the actual distance in d in feet of the ball in t seconds when it's fired from the cannon. Um, so again, we're talking about gravity from the other lessons. Remember we talked about Galileo. So what would you get if you were to get an equation out of this? So hint, remember the 16. I should not probably use n. I should probably use t for time. That's a thing. So that's my hint. Go ahead and try to create an equation um, with your group. Now, there's three things to consider though. Where did it start? All right, what altitude did it start? And what does and mean in algebra? And what was its speed per second? And what's the gravitational pull of the planet with t squared? Okay, so that's your hint. Go ahead and try to create an equation, and yes, it's definitely going to be quadratic. So pause the video and we wait. Okay, so hopefully you pause the video like I requested and you realize that, let's see, let me scroll down. There we go. All right, so hopefully you pause the video and you realize that the gravity is going down, right? The ball is going down. So your distance, well, you start off with 10 feet up in the air, right? Like you're on a hill or something. And, aka plus, you're traveling 406 feet per second as time goes by, right? But as time goes by, gravity starts taking away from your altitude. Okay, so here's the gravitational pull of the planet as time flies by squared. So that would be your first actual quadratic formula, written in standard form. Of course, it's not in order, but that's because the context started with the height of, so this is the starting height. This is the velocity, and this is the gravity. Those are the three things you need to take into consideration when we're talking about flying projectiles on a planet or near any celestial star or body, I should say. Yeah, asteroids work too. Okay, moving on. Graphing another cannonball. So we have another cannonball here. All right. And definitely go over with your group of what just happened in the previous one for 6.2. All right, so graphing another cannonball, 15 minutes. They give us this function. So my question for all of you is, what does this 50 mean? What does the 312 mean about this cannonball? And what planet would you say that is uh, telling you what the gravity is? All right, so what do those terms mean about the cannonball? And that's very much context. All right, and go ahead and look at the previous example. All right, so pause the video, try to figure out what those tell us about this situation for this cannonball. So pause. Okay, so hopefully you stopped and discussed this with your group. And 50 was the starting altitude in which the cannonball was fired. 312 is its velocity. All right, I'm assuming feet per second, right? And gravity is negative 16 feet per second squared. All right, so that's your planet. Now, what I want you to use is I want you to use Desmos as your graphing technology, and I want you guys to go ahead and type in this function. If you need to, use Y for D and X for the T's, okay? And make sure you set your domain between 0 and 25 and your range from 0 to 2000. And then look over the graph with your group and discuss what you guys see. So describe the shape of the graph. What does it look like? All right. What does it tell you about the movement of the cannonball? So the graph itself does tell you a kind of a story or a sketch of what to expect to see from the cannonball. All right. In part B, tell me where the maximum height is. All right. And then when does that happen? So when on the x-axis, all right, does that happen? All right. And estimate when the ball hits the ground. So you can see all those three things if you use Desmos. So make sure you do that because that's something you need to be able to do. All right. And then what domain is appropriate for this function? So looking at your x values, what would make sense for that cannonball? You're not going to tell me it's going to exist in negative 5 seconds, right? You fire the cannonball at 0. So hint, hint. All right, so go ahead and pause the video and try to figure that out on your own. It's going to take some time, but Desmos is going to definitely going to help you. So go ahead and pause. All right, if you paused, you should get something like this, right, on Desmos. So you probably had to scroll in, scroll out, and kind of play a little bit with your domain and range. But they did recommend 0 to 25 for your x, right? And then for your y's, they said from 0 to 2000. And that should have helped to give you this. Now, how many seconds did this cannonball take to get to its highest point? And hopefully you realized, boom, right there, right? So 10 seconds. Okay, and these are the answers that should be going up on the top part. This point right here, by the way, is called your vertex. All right, it's either the highest or the lowest point of your parabola. And the parabola is that entire curve, that bell-like shaped function. Okay. Now your zeros. Um, you fire the cannon on the cannonball right here, right at 0 comma 50, right, and then it lands somewhere over here. Wherever your cannonball lands, and even if it's on the ground where it takes off, these are known as your zeros. All right, and that is basically when x, your x value, I'm sorry, not your x value, that's usually when your y value equals 0. All right, so those should have answered your questions for those situations. So, what the shape of the graph? What does it tell you about the movement of the cannonball? And hopefully, you guys said what comes up must come down, right? And that's just basic understanding. It's kind of funny if you actually look at old graphs of cannonballs back before calculus became a thing. They didn't draw a curve like that. They basically just said your bullet or cannon flies up and then it just drops down. I'm not kidding. Like your old school graphs back in military history, your cannonballs literally went like if you fired a bigger cannon, like a faster cannonball, they were like, oh, it goes out farther like this, but it still falls down. That's literally what the graphs look like back in the day before um, certain people came across calculus, and it's kind of a rough time for us as a human species. All right, so let's move on. Cool down. So rocket in the air for 5 minutes. This is purely for you. I'm not going to spoil this one. Definitely try to work on these ones together. Again, still talking about, I believe, it's a rocket. Okay, but you could already look at the graph and kind of know the story, right? So cannonball, rocket, doesn't really matter, does it? It all has the same relation with gravity uh, due to its variables of time and speed. All right, so classwork, go ahead and work on your classwork. You guys have a beautiful day, and I will work on this sore throat. All right, take care of yourselves. Again, if you have any questions, I'll be back on Monday. Bye.